Hello, everybody. So I want to do an example of an iterated integral. We did one in the last video, but it would be nice to do at least one more. So here's the problem. I want to find the volume under the surface f of xy equals y e to the negative xy over this region R, which is the rectangle with all values of x from 0 to 1 and all values of y from 0 to 2. So let's just jump right in. We're going to do this algebraically, and then we'll take a look at a picture of what we're doing when we're finished. So let's start by writing, right, the symbol for this is we're looking for, right, we're trying to compute this. This is what we decided is our symbol for the volume that's being asked for here, right? Now remember, in general, we're including in volume the notion of a negative volume that can have different interpretations depending on the function. In this case, everything's positive, or at least non-negative. We'll have some zero values when y is equal to 0, but otherwise everything's going to be positive because we're looking at positive values of y times an exponential, which is always positive. So we can solve this using our iterated integral, right? So I can look at the bounds in terms of x, the bounds in terms of y e to the negative yx, dy dx, right? And the idea, again, is I'm going to look just at this piece in the middle first and take an antiderivative, or a definite integral with respect to y, right, treating x as a constant. However, looking at this integral, I notice I will have to use integration by parts. And it's totally doable, and I encourage you to try that. I'm going to use the fact that according to Fubini's theorem, that if these exist, they're going to be the same. I'm going to change the order of integration. Right, so now I'm looking at doing the x derivative first. Okay, it's not always the case that one way is easier than the other, though it often is. It's not always obvious either. I'm making this choice simply because parts adds a layer of complication. There's already a lot of moving parts when we have to sort of think about x on its own and think about y on its own. So I want to see what happens if I do it in terms of the x. I don't think it's going to get worse, and maybe it gets better. So let's do an antiderivative off to the side. So I'm trying to take, I need an antiderivative with respect to x, treating y as a constant. So since y is a constant, it can slip on through. What do we get? The antiderivative of an exponential is itself, but we have to think about the chain rule. We would need, maybe it's even helpful to do something like this. This, right, we would have negative 2x, but we need a negative 1 over 2 as an antiderivative to counteract taking a derivative and having this chain rule pop out a negative 2, right? So if you kind of think back to integral calculus, that might help. In any event, what we need here is a negative 1 over y. And again, I'm ignoring the constant of integration because I don't need it to do the definite integral. I just want to get the form of the definite integral that I'm going to use. Y times negative 1 over y is negative 1 e to the negative yx, right? So here's my antiderivative, and it's always a good idea, at least in your head, to check, take the derivative of this. We get the same thing, except a chain rule makes us multiply by negative y, which gives us y e to the negative ex, which is exactly the integrand that we want. So there's my antiderivative. So now what do I have? I have negative e to the negative yx evaluated from 0 to 1. This is all happening inside the y derivative. We're going to get negative e, so remember these are x values, negative e to the negative y, minus a negative e to the 0, so plus 1. Right? So there is our antiderivative. Now we have just a function of y, and lo and behold, because of what happened with the antiderivative here, that y sitting in front is gone, and I don't need to deal with that integration by parts that I thought I might have to do. So now we have to just take the antiderivative of this, which is a much easier antiderivative to take, and evaluate it from 0 to 2. So we'll get e to the negative 2 plus 2 minus e to the 0 plus 0, which is e to the negative 2 plus 2 minus 1, or e to the negative 2 plus 1. And that should be the volume of the region of the shape that we're talking about here. Okay, so I'm not going to go ahead and do this parts, but I definitely encourage people to try that and see that you wind up with the same result. You should, unless I made an error in here that I'm not catching. Okay, let's take a look at a picture of this thing. So here is a graph. Here's our surface, right? Pretty fun, interesting kind of shape. And let's look at the region. So now there's this little gray rectangle. That's the region R. X goes from 0 to 1, Y goes from 0 to 2, right? This is kind of the more traditional orientation. It's a little harder to see under there. Here is the piece of the surface above that region. Let's remove everything else. So we were finding the volume between that little patch of XY plane and this bent curved surface. And it looks reasonable what we got, right? It's a little bit hard to tell when you're just looking at these things, but if you notice, for instance, if, let's put, let me just graph, I'm gonna graph, right? There's a surface that goes up to x equals 1, right? This whole thing would have a volume under it of 2, right? Because there's, it would be a 1 by 2 by 1 box. Our volume was 1 plus e to the negative 2, or 1 plus 1 over e squared, which is like somewhere between a quarter and a ninth, so just barely bigger than 1. It seems reasonable. Maybe I'll bring this volume down, right? Here's a volume of 1/2. Sorry, this whole thing would have a volume of 1, and it doesn't seem unreasonable to think the bit of volume at the back would fill in most of this, the pieces that were missing in that box, plus a little bit more, right? I'm just eyeballing it to see if I'm in the right neighborhood. Certainly if I got a volume of something like a volume of, say, right, here's a box up to 2. This would be a 1 by 2 by 2 box, has a volume of 4. So if my computation gave me a volume of something around 4, I would be highly suspicious, because I certainly don't look anywhere near that volume, right? My volume certainly has to be less than the volume of the box up to that ceiling. So in any event, I just wanted to give us a little picture of what we're looking at here. The volume under this curved shape. Okay, that is it for this one. Thanks, everybody. See you next time.